welcome to video 1 of our discussion on buffers and titration systems. This is going to be furthering our understanding of acid-base equilibria and basic and acidic salt equilibria as well. So we need to ground back into something that I think kind of got lost in the acid-base unit, and that's about neutralization. Anytime you put an acid and base into the same container, the same system, strong or weak, the hydroxide and hydronium ions are going to react completely until one or the other or both are gone. And if you think about it in a strong acid, strong base system, that's kind of easy to understand. You imagine a hydrogen ion and a hydroxide ion nearby, they're going to react and form water, because you know that the concentrations in a 25 degrees Celsius container of water of hydrogen and hydroxide are really, really small, which means you're going to have to keep in mind that this formation of water happens with fidelity. Okay, so what remains of hydrogen and hydroxide is going to be insignificant in just plain old water. So in an acid-base system, when tons of these ions are around, they're going to react aggressively to form new water, regardless if it's strong or weak. And the way you can think about a weak system is just imagine the two systems side by side with a certain number of hydrogen and hydroxide being placed into the system by the weak acid or weak base equilibrium. Just some number of hydrogen and hydroxide being placed into the system. More than is going to be put in by the water itself. And so what's going to happen is the hydrogen and hydroxide from the weak acid, weak base are going to immediately react and form water. And that's going to happen precipitously until all that acid or base in those original forms are gone according to their equilibrium. So in a weak acid, weak base system, strong acid, weak base, weak acid, strong base, you can expect them to neutralize one another. Okay. Now, whether that leaves you with a salt system that puts pH above or below 7, that's going to be depending on the system. But as far as acid-base neutralization goes, you can expect those systems to react completely. Going back to the common ion effect, we have to keep in mind that adding a common ion will shift equilibrium. When we go by Le Chatelier's principle on this, if we put hydrochloric acid into plain old salt water, dumping tons of this ion in, because keep in mind, a strong acid dissociates completely, lots of chloride is all of a sudden there. And we're going to change the solubility of sodium chloride, and we're going to probably precipitate crystals. We would not expect normally to see this kind of thing happen, but you can precipitate sodium chloride salt if it's a nice concentrated saturated solution with hydrochloric acid. Pretty fun little experiment there. So continuing on that idea, for a weak acid system, we can imagine that if we had acetic acid in water, if we dump sodium acetate into the system, we can expect to raise the pH, because what's going to happen is the hydronium of the system is going to be consumed along with acetate to form water and the intact acid. We can also calculate the pH of the system using the Ka for the weak acid itself. So there we are adding our salt in. We would expect our system to respond by pumping towards the reactant side. Going back to the Q versus K argument, when you increase the concentration of products, you're changing Q to be larger than K, which is going to shift your reaction back towards reactants. So here's an example where we have a solution of hydrofluoric acid and potassium fluoride, 1 molar, 1.5 molar. What's the pH of the solution? Now, I haven't told you this yet, but this is a buffer system we've built. Okay, we have a weak acid and we have its conjugate base, the fluoride ion, available in the solution. This value for Ka we have. So we start off with our initial concentrations given in the question, here and here. We remove some of the hydrofluoric in favor of ions, and then we end up with our equilibrium expression. We plug all that into the Ka. We neglect our X's, because that's where we are now. And we calculate a new concentration for hydrogen ion, which is equal to X. That gives us a pH of 3.32. In our buffer system, we have a pH higher than it would be if we just had a hydrofluoric acid system. And that stands to reason. Just like in the previous slide, we have added in lots of fluoride to our what would have been just a dissociation equilibrium. That extra fluoride consumed hydrogen, made more intact hydrofluoric acid molecules, which drove the pH up. Okay, so the question says, what did adding the salt do to the pH of the system and why? Well, we added the salt potassium fluoride, which added product ions into the system, which drove the equilibrium back towards the reactant. And the reason for that is when you increase the concentration of products, your system's Q is larger than K. The system will react by consuming those products to make reactants to return the system back to equilibrium and restore the K value. I didn't mention this, but the 1.57 in that value here is calculated from the Ka itself, imagining that there was 0 fluoride in the system at the same time. So the 1.57 pH is just the hydrofluoric acid system. So a buffered solution, what is it? What buffers? You hear it from high school students, and they say it like it's a bad word. Ultimately, what it is a solution of a weak acid, or you can make a basic buffer if you want, a weak acid and its conjugate base, here also listed as a weak base. A buffered solution is a solution that resists the change in pH when hydroxide ions or protons are added to the system. You can add acid to it, you can add base to it, and it will keep the pH relatively constant. A buffer solution usually consists of a solution of a weak acid and its salt, or a weak base and its salt. A great example, your blood contains the carbonate buffer system, which keeps your bodily pH, give or take 0.05 of a pH. And that big of a swing even could cause you to have to go to the emergency room. Your body is a fantastic set of buffers. So what does the word buffer mean, and how does it apply to what we know already? Okay, so if we look at a diprotic dissociation titration, this would be something like carbonic acid or sodium carbonate in an acid maybe. The buffer system is when you have a meaningful concentration of a weak acid, in this case like a carbonic acid or hydrogen carbonate ion, and its conjugate base. Those two things together work in concert to neutralize any acid or base threat. And of course there's a quantitative limit. With any buffer system, there is a limit to how much the system can take before it basically destroys the buffer. What you see happening here is that this is completely carbonic acid in solution, and then we begin to watch the system deprotonate because of some basic threat. And what we see initially is we have one flat portion here, and this is the buffer portion. This is where we have a weak acid, and we have its conjugate base present in decent concentrations. And we have another minor one here. Okay, those buffer system components are the places in which it's relatively difficult to change pH. So you need to, in a buffer system, have those two things there. You can't just have hydrochloric acid and call it a buffer. If you add hydroxide to a hydrochloric acid buffer, hydrochloric acid system, it'll change. If you add acid, it's probably not going to change much. But what you don't have is a system that's fairly stable under threat of either. So you're looking for a weak acid in its conjugate base, or a base in its conjugate acid. So here's some imagery of the acetic acid acetate buffer system. If you add a strong acid to the acetic acid, and this is the intact acetic acid, and to the acetate buffer system, if you add an acid, protons, to this, what's going to happen is your conjugate base, your acetate ions, are going to make the intact acid. Okay, so your acetate's neutralizing. And we're using hydrogen here to make it evident what's happening here, but this is a model where we have hydrochloric acid being dropped in, and you see that those chloride ions go into solution, and some of those acetate molecules react with and form some of the intact acid, acetic acid. If we look at the other side of it, if you were to add sodium hydroxide to an acetic acid acetate buffer system, your acetic acid would neutralize the hydroxide. Okay, and so here's our drawing of sodium hydroxide, for example. The green would be the sodium, the hydroxide would be the light blue. What's going to happen is our system is going to neutralize that by using the intact acetic acid molecules, which you can see here, and they're going to interact with the hydroxide component and make intact new water molecules. Okay, so either component can help stabilize the pH of an acid or base threat. This is a different buffer system, the ammonia and ammonium ion buffer system. Same thing. If you add an acid, your base ammonia will interact with it. If you add a base, your conjugate acid ammonium will interact with it. So we have to mention buffer capacity. Buffer capacity is the amount of acid or base that can be absorbed by a buffer system without a significant change in pH. In order to have a large buffer capacity, the solution should have a large concentration of both buffer components. concentration of weak acid and conjugate base, and large concentration of weak base and conjugate acid for the opposite. What's not mentioned here is you want those values to be about the same. So generally speaking, for a particular buffering system, all solutions that have the same ratio of conjugate acid and acid will have about the same pH. Now this means it's got to be acetate and acetic acid, or ammonia and ammonium, but it's got to be the same system. But if you keep those conjugates and acid concentrations the same, then the pH, regardless of what else is in there, is going to be the same. Now, buffering capacity could be very different. We could have 3 molar ions and 3 molar acid and have the same pH as a 0.1 molar and a 0.1 molar. Let me write these out so you can see what I mean. These, if they're the same by ratio, then the pH of these two solutions would be the same. We can work this out later on. I'll show you how. But the buffering capacity of this would be very small. We'll call this buff cap to simplify my writing. This would have a much smaller buffering capacity because we have much smaller concentrations of the acid in its conjugate base, whereas we'd have a large buffering capacity here because we have larger concentrations of the acid and conjugate base. So optimum buffering occurs when you have equal concentrations of the acid and conjugate base. That means your system can react to either acid or base ably. And of course, when we have large concentrations of each ion, those are the ways a buffer is going to work the best. It's important to note that if you're trying to make a solution of particular pH, the pKa of your weak acid should be as close as possible to the desired pH of your buffered system. So if you want to keep a buffered system of 4 for a specific living organism or a particular chemical process you're working on, you need to make sure that the pKa of the weak acid system you're working with has a pH, or is very similar to the pH that you desire. So if you want a pH of 4, you need to choose a weak acid with a pKa of about 4. Okay? How can I make a buffer? Okay, so Mr. Crump, this sounds like so much fun, but I want to make one at home. Okay, great. That sounds like a plan. So what do? You're going to mix a weak acid and its conjugate base together. That's one way. That would mean like you go to the grocery store, you buy some vinegar. That's a weak acid. You go to the pickling store and you get pickling salt. If you're lucky, you're getting sodium acetate and not sodium chloride labeled as pickling salt. And you put those two things together and you have yourself a buffer. Okay? There's lots of ways to make buffers, though. That's not the only way. Another way is you could take your weak acid, you could take your vinegar, and you could add a little bit of strong base, like sodium hydroxide, I don't know, drain cleaner, just a tiny bit. Of course, you would have measured all these things, and you're not actually going to do this in your house without supervision of a chemist, because that would be dangerous, and wow, that's crazy. But the thing is, if you take a weak acid, and you add a little bit of strong base, that strong base is going to create some of your, this is written wrong, some of your conjugate acid. I'm sorry, no, that's true. Some of your conjugate base. Can you imagine you had your HA, your weak acid, and you add to it hydroxide? What's going to happen? You're going to make water, and you're going to make conjugate base. Okay? So you can have a weak acid mixed directly with the conjugate base, in the case of sodium chloride and sodium acetate. Oh, sorry, hydrochloric acid and sodium acetate. Or you could take your weak acid, acetic acid, and add some strong base to it to come up with your conjugate acid all on your own. This is not acid, this is base. It was correct. Let me erase that so nobody's confused. This was correct. So this is also true for vice versa. So if you take a weak base and mix it with a strong acid, you can create a buffer. If you take a weak base and its conjugate acid and mix them together, you make a buffer system. So at this point in your learning about acid-base equilibrium, we would normally turn to the old and familiar rice table and rewrite the equilibrium expression with our unknown value, but watch what we do in the next video. The next video is going to show us a simpler way to work with the math of an equilibrium system and give us a clearer understanding and a shorter path to doing some of the math we have become accustomed to doing. I'll see you in the second video. Ciao.